Okay, we are going to start chapter 5 today. This is the chapter that starts taking a look at probability, which is typically a tricky subject for students. So we're going to look at some just basic principles of probability here today. This idea of probability is really this notion of you having a chance behavior that is unpredictable in the short run, okay? Unpredictable in the short run, but it's a very regular, predictable pattern in the long run, okay? So if you were only to perform a certain event just a small number of times, you would find that your results would likely be unpredictable. But if you were to repeat those events many times in the long run, you would notice that there would actually end up being a very regular and predictable pattern, okay? And we're going to take a look at what I mean by that here in just a moment. So when we refer to probability, and you're probably aware of this, that's any outcome of a chance process that is some number between 0 and 1. Okay, so if it's 0, obviously we're talking about the likelihood of it occurring would be never, and if it's 1, we're talking about the likelihood that it would occur would be always. Okay, generally probability then is some number in between 0 and 1. Okay. Keep in mind that probability is always referring to what will happen, okay, not what's happened in the past. Probability is always looking towards the future and what will happen. Okay, so there is this notion called the law of large numbers, okay, the law of large numbers. And what the law of large numbers is it says that if we were to observe more and more repetitions of any chance process, the proportion of times that a specific outcome would occur tends to approach a single value, okay? And so what I'd like you to think of here, and we would have done this simulation here in class using this applet here online, but I want you to think about a coin, okay? Not a trick coin, a fair coin, and think about what the likelihood is of getting heads on just a single flip, okay? That is obviously 1 out of 2 or 1/2, okay? And then we think, well, if we were to take that coin and say we were to toss it 10 times, how many times would we expect to get heads? Maybe we would expect to get 5 out of 10, but we know that if we were to do this, we're only flipping the coin 10 times. It's very likely that, maybe sometimes we could get heads 6 out of 10 times, or maybe if we were to do it again, maybe only 2 of the 10 flips we got heads. See, flipping a coin 10 times is not doing or performing that event repeatedly over and over many times, okay? So you notice a lot of variability when you are only performing an event a short number of times. And so what this little graphic is showing you is the y-axis is the proportion of heads, okay? So apparently with the very first flip, it was heads, and that's why we're up here at 1, and then the second flip and so on. And what you notice about this is the more flips, so this is the number of flips. So all the way over here, we're talking about flipping the coin 100 times. You'll notice that the average here of getting heads, do you see how it's starting to level off right at about 50% of the time we would expect to get heads. And so the more you increase the number of events, the more you're going to notice that that's going to flatten out. And that's what we're referring to when we say that probability, it's unpredictable in the short run, but if you were to do it repeatedly in the long run, you end up seeing that there is a predictable pattern there. Okay. Now there are some myths that tend to crop up when we talk about probability, and so I just want to discuss these with you here. The first one's called the myth of short run regularity. Okay, things aren't typically regular if we're talking about short run, meaning only a few trials. Okay. It says here the idea of probability is that randomness is, and I'm going to insert the word only here, randomness is only predictable in the long run. Okay, truly, when we talk about that with statisticians, we talk about long run. We're not even talking about 100 or 200 trials. We're talking about like 1,000,000+ trials here. Okay, that's when we can start to make pretty accurate predictions about what would take place. Probability in and of itself, though, it does not allow us to make any predictions on the short run. Okay, so another myth here is called the myth of the law of averages. Okay, the myth of the law of averages. Okay, now what's true is that probability does tell us that random behavior evens out in the long run. Okay, so I'm going to make sure this is clear that this statement here is true. Okay, but sometimes, we'll take a look at this here in a second. Okay, let me go ahead and highlight this. It says future outcomes are not affected by past behavior. And that's what some people confuse this myth of law of averages to mistakenly think that what has happened in the past is going to impact what happens in the future. Okay, let me give you an example of this. Let's go back and say that we were to take a fair coin, and let's say that we were going to flip it 10 times here. Okay, and what you see in each of these three scenarios here are the recorded outcomes of whether it was heads or tails on each of those 10 flips. Okay, and you can notice here, there was a mixture. Here the first 5 were heads and the last 5 in a row were tails. And in this situation, they were all heads. Okay, the question is, which of the following outcomes is more likely when you're flipping the coin? Okay, now this might be surprising, but actually all 3 of these scenarios, all 3 scenarios are equally likely. Okay, all 3 scenarios are equally likely. Okay, and so what some people wrongly believe is they wrongly believe that if a chance process turns up a single outcome multiple times in a row, the probability of getting a different outcome increases. Okay, now it is true that in the long run, things tend to even out. But keep in mind, when we're talking about long run, we're talking about 1,000,000+ trials. Okay? So you want to just kind of remember that when we are talking about like coins and dice and even roulette wheels, those are not living things. They don't have a memory. So when you flip a coin, that coin has no knowledge or recollection of what happened to it in the previous flips. So it's not thinking, I just got 5 heads in a row. I better make sure that these next ones I land on tails so that I can kind of make this end with 50-50. Okay? So here's a great example of a mistake that some people make here. Okay, they think that if you are in a family and you have had 4 girls, that the chances of your 5th child being a boy is much higher than 50%. Okay, you have a 50-50 chance of having a boy with every single individual pregnancy. Okay, whatever gender has happened previously, that doesn't matter. Okay, so if you have 4 girls, the odds of you having a boy in the next pregnancy is just 50-50. Okay, it's not a higher probability. Okay, all right, let's go ahead and flip here to the next page. Okay, and we'll take a look at a few examples here. Okay. It is going to be important, particularly on the homework assignments in this section, that whenever you are interpreting probability, okay, you always want to make sure that you are framing that interpretation in the context that the sample has to be a large sample, meaning you would be repeating that trial over and over and over again. So it has to be a large number of trials. Okay, it has to be a lot of them. And that this is because the probability is only predictable in the long run. Okay, so for this first question, it says, according to the Book of Odds website, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Part A says explain what the probability 0.61 means in this setting, okay? So they're asking us to interpret the probability, okay? So we want to say, well, if you asked, okay, now not just a single U.S. adult, but we're talking about you would have to ask a large sample of adults. We want to make sure that we're getting in there that the only way that this is going to be predictable is if we have a large sample. So if you asked a large sample of adults whether they eat breakfast approximately, okay, it's good to put the word approximately there because the odds of exactly 61% of them saying yes, they eat breakfast is unlikely, okay? So two key words in this. One, we want to make sure that we're talking about that we asked a large sample, okay? And two, that we put the word approximately in front of the 61%, okay? But you definitely want to make sure that you start out your interpretation with if you asked a large sample of adults, not simply, oh, there's a 61% chance that an adult says yes, they eat breakfast. Well, that's actually only true if your sample was extremely large. Okay, let's look at part B here. Part B says, why doesn't the probability, why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? Okay, so that word exactly is what we want to hone in on, okay? And we're just going to say, well, the exact amount varies from sample to sample, okay? So that's why we always think of probability as a long-run average, okay? A long-run average, because it does vary from one sample to the next pretty dramatically. Okay, what we're going to move into, and this is going to play a big part in stats that we're looking at in the second semester. So we want to get introduced here today to what the aspects of performing a simulation are. And so we're going to talk through some of the pieces to this, and I'm just going to walk through one example where most of these pieces are already done for you. These problems, again, are pretty involved, and the key with this is us explaining what the procedure would be so that you could hand the description of your procedure to someone else who probably doesn't know that much about statistics and they could execute your plan. Okay, so let's talk about what a simulation is first. It says the imitation of chance behavior. So when you're performing a simulation, you've probably heard like, oh, let me simulate that. Okay, that means you're going to imitate that. Okay, so we're going to imitate a chance process, okay, based on a model that accurately reflects the situation. Okay, that is called a simulation. Now, simulations are usually done with a table of random digits, a calculator's random number generator, or some type of computer software. For us, it will either be a table of random digits or the random number generator on the calculator. Okay, there are four aspects to a simulation. The first one is called state, and that's when you're basically identifying sort of what is the probability that you're trying to simulate and calculate. The second step is the plan step, and this is where you get into a lot of the details of describing how you plan on using either a table of random digits or the random number generator on your calculator to implement one repetition of that process, and you're going to clearly explain how you would identify your outcomes. Okay, and we're going to look at an example of this so that you'll see this in action. The third step is the do step. Okay. Now remember, we said things are really only predictable if you do them in the long run. I'm not going to have you do these simulations a million times, but performing a simulation once is not very beneficial. Okay. Typically, we would want to do it at least 20 times. I think in your homework, I'm going to have you, I have it listed for you to just do it 10 times. It does get repetitious, and so for the purposes of your homework, I will have you perform the simulations 10 times unless the directions for the problem say otherwise. And then finally, after you've performed the simulation repeatedly, then you will draw a conclusion. You will use your results of your simulation to answer the question of interest, and very important that that is always answered in the context of the problem. Okay, so let's look at an example here. It says, what's the probability that a student would earn at least an 80% on a true-false quiz that was written in Chinese? Okay, so if I gave you a true-false quiz, let's say that it had 10 questions on it, and you cannot read Chinese, okay, we're going to assume the exam taker does not know any Chinese, what is the likelihood that you could essentially guess your way to getting an 80% on that true-false quiz? Okay, so if you get at least an 80, that would be 80% or higher. Should the instructor be concerned that you may have cheated? Okay, and so what we're after is we want to try to simulate the likelihood of someone guessing 80% or more on this true-false quiz and getting it right. Okay. Now remember, here are the required elements for a simulation. Okay, and I've got them kind of broken down here. State, plan, do, conclude are our 4 steps. Okay, and then underneath each of these, I've just listed very generically, this is not specific to this example here, but I've listed the different elements for what you would do in these steps. And we're going to come back and revisit this Chinese true-false test here at the end of these notes in the next video. But when you're doing the state step, you want to identify your variable and state the probability using either symbols or words. In the plan step, you're going to define what tool, random number generator, table of random digits that you're going to use, what values you're going to be assigning, how many times you're going to perform the simulation. Again, think of this as a written plan that you could hand to someone, and then they would be able to follow through with your plan. So if you're not clear and you don't specify the details, they're not going to know what they should do, what they should record. Okay, so let's go ahead and look at a problem here. We will just do this golden ticket problem, and this will be where we'll stop here on this video. Okay, the golden ticket problem is this idea that we have a local high school and 95 students have permission to park on campus. Okay, now each month the student council holds a golden ticket parking lottery at a school assembly. Okay, now so let me just kind of box in a few important pieces of information as we read. We know there are 95 students who can park on campus. It says here 2 lucky winners from this lottery are given reserved parking spots next to the school's main entrance. Okay. Last month, the winning tickets were drawn by a student council member from the AP Statistics class. When both golden tickets went to members of the same class, some people thought the lottery had been rigged. Now, there are 28 students in the AP Stats class, all of whom are eligible to park on campus. So here's what we have here. There's 95 students in the lottery. 2 winners are selected to get these prime parking places. And the 2 individuals that were selected from these 95 were 2 students from this 28 student class of AP Stats. Okay, and so I think some people are thinking, hey, this is unfair, this is rigged. The student council member who drew them out was from that class, and they kind of rigged it so that those 2 individuals that were chosen came from that class. Okay, and so again, in this box underneath, these are the 4 components anytime you are drafting a simulation, and I have most of this sketched for you, so we're just going to kind of read through this so that you can see this in action here. Okay, the state process, specifically to this example, would be stating what the variable is and then state the probability in symbols or in words. So we could say, what's the probability that the lottery would result in having 2 winners from the AP Stats class? That's what we're after. What's the likelihood of what just happening by chance? Getting both winners that happen to come from that AP Stats class. Now, how could we use symbols to say that? Well, putting a P with an X equal 2 and defining that X represents that the winners are from, like the number of winners from the AP Stats class. This is saying we're looking for the probability that X equals 2. Okay. Now, for the plan step here, okay, the plan step, I've answered each of these questions here. It says the tool that we're going to use, and we could either say a table of random digits or a random number generator on the calculator. Okay, we're going to assign values 1 through 95. Okay, and what you see here is this is me answering each of those questions. I'm just going to write here that is optional to write it out like that. It's much better to write the plan explained. Okay, but if it helps you to write it out like that first, you can do that. Okay, so I'm just going to take these elements that are above and I'm going to write it out in an explanation here so that I could hand this to someone and they could follow through. So I'm going to say, using a table of random digits, we will randomly assign each student a 2-digit number from, remember we said before that when you are randomly assigning when you're using the table of random digits, you always want to make sure that you have the same number of digits. So it's 01 to 95, okay? We will label the students in the AP Statistics class from 01 to 28. So any numbers from 1 to 28 represents a student in AP Statistics. If it's 29 to 95, those are the other students who are eligible to win the parking spot, but they're not from AP Stats class, okay? So the remaining students, and then we'll label the remaining students 29 to 95, okay? Now, you should mention what happens if we run across a number in our table and it doesn't fall between 0 and 95. Well, then I'm telling the person, look, any numbers from 96 to 00 will be skipped, okay? From 96, so 96, 97, 98, 99, and 00. Skip those. Starting at the randomly selected row 139, okay, and moving left to right across the row, we will look at pairs of digits. I mean, do you see how detailed this is? This is really spelling this out. Pairs of digits until we come across two different values from 01 to 95. With these two values are going to represent the 2 students with these labels who will win the prime parking spaces. We will record whether both of those winners are members of the AP Stats class by either saying yes or no. And we're going to conduct this, it says 18 times, okay? So here's what we're after. What is the likelihood that not just one student chosen was from AP Stats? It has to be both of the students. That's why I'm only saying yes if both of the numbers were from 1 to 28, okay? All right, so to wrap this up, let's look at the next page, and I'm going to have us go through the do step. Here's what I've included down here. I've included row 139 and row 140 from the random table of random digits that are in the back of your book. Okay, here's our explanation. We're assigning the AP Stats students numbers 01 to 28, everyone else 29 to 95, skipping anything in this window here. Okay, so I'm going to repeat this process 20 times. Okay, so what you see underneath here, and I'll just walk you through this here, I'm going to block off the first 2 digits. That is person number 55. Okay, and then I'm going to pick my second winner. That's person number 58. Okay, neither of them were from the AP Stats class. I'm saying no because they both were not from AP Stats. Okay, then I'm going to block off the next one. I've got 89, not from AP Stats. 94, that's also not from AP Stats. I'm going to say no. Okay, so you kind of see the pattern here. I'm writing down the 4 digits. Now, if I get something that is outside the range, let me keep going here till that happens. So here we have 70. Okay, now 04, that student actually is from the AP Stats class, but this student that's the 70, they are not. Now I'm only saying yes down here if both of the students selected were from the AP Stats class. So I'm going to repeat this process 20 times. Okay, there's enough places here, 20 times, and I want to see out of 20 simulations, what is the likelihood that both of the students would have come from the AP Stats class. Okay, so just to kind of push through things here, I'm going to go ahead and fill these numbers in very quickly. Okay, I think you can see where I would be getting these from. Okay, and we're just curious, like, is this something that could happen by chance? And remember, our benchmark in statistics is that 5% mark here. Okay, so I'm going to fill these in here. We're getting closer to 44, 72 to 32. There have been some along the way that, you know, if you actually went through and made your vertical bars here, that you would throw out and disregard because they would be in that window between 96 and 00. But the ones where they were both from AP, it actually didn't happen until the very end, the last couple simulations. Those two students and these two students were both from the AP Stats class. Okay, so how often did it happen? Well, oh no, it happened one other time too here. I think it also happened right here. Okay, so it happened 3 times. So we did this, oh, not 20 times. I think we did this 18 times, okay? So we're going to record down that based on our 18 repetitions of our simulation, both winners came from AP Stats class 3 times, okay? So that means the probability is 3 out of 18. There is actually a 16.67% chance that just randomly 2 students could be drawn out of those 95 and that they both would have come from the AP Stats class. So it's definitely possible for this to happen in a completely fair drawing. We should not be alarmed or call anyone out that they rigged anything. Now, had this number been a number that was under 5%, that's when we should start being alarmed and think, the likelihood of this happening is so small that someone must have rigged the drawing. Okay, that's where we're going to stop. Again, you can see some little markings here on 25 and 28 where you will